Hello and welcome. Today we are going to look at optimization under differential calculus. To find solution to most problems, we have to find minimum and maximum values of some functions. This is known as the optimum solution, and the process through which we arrive at that is optimization. Optimization is used in industry, in medicine, in agri, and then also in the financial sector to maximize profit or to minimize loss using limited or available resources. To start with today's lesson, let's take a look at a student assessment to review our previous knowledge. Find and classify any stationary point in the function f of x is equal to s cubed minus 3x plus 2. Let's take a look at this and try before we continue with today's lesson. This is the solution to the problem we have, learning outcome for today's lesson. By the end of the lesson, the student will be able to clearly identify optimization related problems and then also outline the steps in solving them. And then also the student will be able to solve problems related to optimization with 100% accuracy involved in solving optimization problems. First of all, you have to draw a diagram to represent the situation. And then also you have to set up a formula or a function in the variable to be optimized. The third one is to find the first differential of the function and set it to 0. That is in case you want a maximum or minimum. The next one is to solve for the variable to be optimized and then also later obtain the optimum solution. Now, let's take an illustrative example. A 4,000 centimeter cube box is to be made. They must have a square base, vertical sides, and then an open top. Find the most economical shape which minimizes the surface area of material needed. And as we can see, there is a diagram which displays what they are trying to let us do. We have a box with a square base and then also an open top, and then also we have the vertical side. Now the solution. From the box, we have the volume to be equal to length at breadth times height, which of course is what? V is equal to L squared times 1. The volume of the shape is given to us as 4,000 centimeter cube. So therefore I have 4,000 is equal to L squared 1. I am supposed to minimize the surface area. So it means that I have to find an expression for the surface area, which of course is given by L squared plus 4x1. Now, since I'm supposed to minimize this one, I'm supposed to have an expression in terms of a single variable. So in that case, I have to find a way to eliminate the y and then make the area in terms of x only. So I have from the first equation y is equal to 4,000 over x squared. So I'll come to the area, which means that I have a is equal to x squared plus 4x, and then in place of the y I write 4,000 over x squared. So finally I have the area to be equal to s squared plus 16,000 over x. At this point, I want to find minimum, so it means I have to differentiate the area with respect to the variable x. So the ADS gives me 2x minus 16,000 over x squared. At this point, I have to set the ADX to 0 because I want minimum. So setting the ADX is equal to 0, I have 2x is equal to 16,000 over s squared, which simplifies to 2x cubed is equal to 16,000. And then also I have s cubed to be equal to 8,000. So therefore x equal to the cube root of 8,000, which gives me x equal to 20 centimeters. If x is 20 centimeters, by all means, my y is equal to 10 centimeters. So therefore, if I want to have the minimum surface area, these are supposed to be the dimensions of my box. Let's meet some other time for more examples. Thank you.